So on the two problems that I gave you, it has listed out what you need to find. But if it's not, if you just were told to, say, find the current for any time t, for an inductor, you're going to use this, IL of t equals IL at infinity plus IL at 0 minus IL at infinity times e to the minus 1 over tau t. And so that means what you would need to find is I at infinity, I at 0, and the time constant. Now in this particular problem, we also have to find some voltages just because they ask us for them. But if they did not ask us for them, we would just need to find the currents. So the first thing that we do is we look at what the circuit looked like before the switch, because this will give us I0 minus, which is the same as I0. So at 0 minus.
We did that, like let's say we were asked to find your current IL.
Mm-hmm.
We would do that, we would look at before the switch, always. Okay. Even if it's
Yep. You look, because that's the only way to find IL of 0. Because if you just look at it after the switch, you're going to make assumptions that aren't true, because it has to be the same as it was before the switch. So at 0 minus, let's say it had been in position 1 for a long time. Now, when an inductor has been sitting for a long time, under DC conditions, it acts as a short circuit. So it becomes a short circuit, but at 0 minus, we can see there are no sources in this circuit at all. So at 0 minus, there's no circuits. So I at 0 minus is 0, and V at 0 minus is also 0. Now, I cannot change instantaneously. This means that I of 0 is 0. We don't know about V of 0 yet, because for an inductor, the voltage can change instantaneously. So we don't know yet what V of 0 is. We know I of 0 has to be 0. Okay, so we have found IL of 0 minus, VL of 0 minus, and IL of 0. We have not yet found VL of 0. So now we're going to draw the circuit at t equals 0. So now we're going to move to position 2.
That's no current because there's no light source.
There's no source. Now, if it was charged, like if it didn't say for a long time, like if it's charged, then you can have a current for a time, but eventually it's going to discharge if there's no source. Okay, so this R1 is 30. R2 is no longer connected, so that's R2. It's not playing anymore. This is 60 ohms. This is 12 volts.
Is there, as we are right now, is there any real situation where we're going to determine the, maybe that's just something stupid, please don't say no.
I think the answer to your question is yes. When you get to the next chapter and you have RLC circuits, you have to find some of these things that right now we don't really need to find.
Well, I was asking, like, 'cause when you first turn the circuit on with an inductor, it has its own current, opposite direction, but we're literally determining that. So
Yes.
it was a dumb question.
Oh, okay. Well, I didn't think it was. If you hadn't explained yourself, I thought it was, I wouldn't have known. Okay, so to find the voltage of something that you don't know, you find something it's in parallel with. And so you can't count on the voltage having anything to do with what it was before the switch because it can change instantaneously. So instead, you find something it's in parallel with. So it still has zero current. And so to me, when I first started doing this, I would think zero current, well, it has to have zero voltage, but it doesn't. It has to have the same voltage as the 60 ohm resistor that it's in parallel with.
Is that at t equals 0?
Yes.
I think she said in class today we're not.
No, you have to.
It's at t equals 0? Because I've never seen it at.
0 plus? Okay, yeah, I don't know. It's there. I mean, it's in the, I mean, it's right here.
Yeah, I think we just. Maybe. I'm just. I'm gonna warn that. I don't know if I've ever seen 0 plus in a problem.
Okay, well, 0 plus and 0 are the same. And so, this is after the switch.
Is 0 at 0 and 0 plus are the same?
Yes. Just after the switch. Immediately after the switch. Okay, so it's the same as the voltage of the 60 ohm resistor. And now, if I look at this circuit, I can see I've got a voltage source. And right now, there's no current going through this inductor. Right at this instant, there's no current going through this inductor. So I can use voltage division to find out the voltage across this 60 ohm resistor here. So V of the 60 ohm resistor equals the total voltage times the resistance of that 60 ohm resistor over the sum of the two resistances, which is 8 volts. So VL of 0 is 8 volts.
Plus they're in parallel, they have the same.
Because they're in parallel, they have the same voltage. Now, that would not be true if I had a resistor in parallel with a capacitor at t equals 0, because I would need to know what the voltage of the capacitor was before 0, because it can't change.
So it's equals 0 because you put it with the voltage, you don't put it as steady state or short circuit.
Right, because it's not. Because right now, it's absolutely not steady state. Right now, it's transient. Okay, so now it's asking for IL at infinity and VL at infinity. So at t equals infinity, so at t equals infinity, now we are at steady state, and it is a short circuit. So there's our inductor. Well, that inductor is now shorting out the 60 ohm resistor. So it's shorting this out. It's a short circuit, and the voltage across a short circuit is 0. And we can find the current just using Ohm's law. So V equals IR, or 12 over 30 equals 0.4 amps. Now I want to find an expression for the current at any time t after t equals 0. And so I of t equals I at infinity plus I of 0 minus I at infinity e to the minus 1 over tau times t. I have I of 0, I have I at infinity. So I at 0 was 0. I at infinity was 0.4. I still need tau. So for tau, I want to look at my circuit the way it looks during its transient time. And I want to find the Thevenin equivalent as viewed by the inductor. And so to find the Thevenin equivalent as viewed by the inductor, I'm going to short my voltage source. And this was 60 ohms, and this was 30 ohms. And this is an example of what I was showing y'all a minute ago. From the point of view of the inductor, these two resistors are in parallel because they're connected at the top and they're connected at the bottom. So R Thevenin, or R equivalent, is product over sum, 30 times 60 over 30 plus 60, which is 20. Product over sum, 30 times 60 over 30 plus 60. Right? They are in parallel. From the point of view of the inductor, they are in parallel. Imagine sliding. Okay. Yeah, you imagine sliding this 30 ohm resistor down to where it's on this side, and then you can see, oh yeah, they're in parallel. Okay, so tau is RC, or 20 times our capacitance was RL, so that doesn't help us because it's not RC. So tau is L over R, and L is 0.2, and R is 20. So tau is 0.01, and 1 over tau is 100. So now I just plug in up here. I of t equals I at infinity, which was 0.4, plus I at 0, which was 0, minus 0.4, e to the minus 1 over tau was 100, t, or 0.4 minus 0.4 e to the minus 100 t. And the last thing that this problem asked us for was VL of t. We needed to find I of t first because that's what we know how to find. To find VL of t, V equals L di dt. So L was 0.2. And then I take the derivative of I. So derivative of 0.4 is 0. Derivative of negative 0.4 e to the negative 100 t is 40 e to the negative 100 t. So this is 0.8 e to the negative 100 t.